Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Equivalence Relations. I encourage you to be active learners and have pencil and paper in hand and use these buttons as you're watching this video. As an example, consider a bag that contains a bunch of balls, and some of the balls are blue, some of the balls are green, and some of the balls are red. You can't really tell, assuming these are identical balls, you can't tell one blue ball from the other, and so one way to describe this bag, or at least the representatives of this bag, are to say, gee, we could have a blue ball, or we could have red ball, or we could have green balls. So you see it's actually a similar kind of description of this, but it's talking about things that are in some sense equivalent to each other. That motivates the following theorem. Let A be a set with a partition, and by the way, we were talking about a partition in that last example because you had blue, green, and red. And let R be the relation induced by the partition. That means the balls have the same color. Then R is reflexive, symmetric, and transitive. Okay. Well, so what we're doing is we're starting with a partition. That means we have A is split up into these disjoint, non-empty subsets. And the relation is this: X is related to Y if there is a set in this such that X in AI implies that Y is in AI. You can think about this as being the balls having the same color. Let's look then at the proof that R is reflexive. So suppose X is in A, and so that means that for some AI, X is in AI. So that means there is a set AI of the partition says X is an element of I implies X is an element of AI is true. That means that, by definition, X is related to X, and that means it's reflexive. Similarly, we'll go to symmetric rather. Suppose X and Y are elements of A, and X is related to Y. Well, that means there is a subset AI of the partition such that X is in AI and Y is in AI. But that means that the same subset will have Y being in AI and X being in AI. So we know that if we assume that X is related to Y, then Y is related to X. And the transitive proof goes sort of similar to that. We say if X is related to Y and Y is related to Z, then X is related to Z. Well, you say that X and Y are in some subset, and Y and Z are in some subset. But Y can only be in one subset, so it has to be the same. So X and Z are in the same subset. And so we have proven that if you have a partition and the relation induced by the partition, then it is reflexive, symmetric, and transitive. And we have a definition for this special relationship. Since they are in some way equal or equivalent to each other, we call this an equivalence relationship. So a relation that is reflexive, symmetric, and transitive on a set X is called an equivalence relation on X. And we can represent them in the same way. We could say, okay, all balls that are blue, we could be talking about the blue balls and green balls and red balls. We have a definition here about what is called an equivalence class. So suppose A is a set and R is an equivalence relation. It has to be equivalence relation to talk about this. For each A, lowercase a in A, the equivalence class of A denoted by, and we have these brackets A, and called the class of A, or the equivalence class of A for short, is a set of all elements in A such that X is related to A by R. So the equivalence class is equal to the set of all X an element of A such that X is related to A. So for every X in A, if X is in this equivalence class, then X is related to A. Now it is important for students to be careful to distinguish between the following. They are different. A relation on a set, the underlying set itself, and the equivalence class for an element of the underlying set. You need to think about that probably for a bit. We have another theorem. Let R be an equivalence relation on set X. For each A, an element of X, let the equivalence class of A, which we know is equal to this, then the set script S equal all of those equivalence classes for X and element A is a partition. You see, we've shown that a partition causes us to have an equivalence relationship. Now we're saying if I have an equivalence relationship, I will have a partition. Okay, so we have to show that every element of X belongs to exactly one element of S. And so we'll let A be an element of X. Since A is related to A, then A is in this equivalence class. Thus, every element of X belongs to at least one member of S. Now it remains to show that every element of X belongs to exactly one member of S. That is, if X is an element of capital X and X is in two of these equivalence classes, then the two classes are the same. Well, we first showed that for all C and D and X, if they're related, then the equivalence classes are the same. Now suppose that C is related to D and X is an element of C, then X is related to C. Hence, those are transitive. The relation is transitive because X is related to D. Therefore, X is an element of D and C is contained in D. The argument the other way is the same, so we conclude that the two things are equal, the equivalence classes. So we have proven this theorem, and that means that if you have a partition, it defines an equivalence relationship, and every equivalence relationship defines a partition. And here is the definition of equivalence classes given yet again. Okay, now if you have then, equivalence classes are partitions, so if you have a set X and you have disjoint subsets, and each subset has R elements in it, then, and since they're disjoint, you just add them up, and so the cardinality of X is R times K. And that really is a proof of this theorem. So if R is an equivalence relation on a finite set, X, then each equivalence class has R elements, and if each equivalence class has R elements, then there are the cardinality of X divided by R equivalence classes, and that follows from the discussion that we've just had. We're going to spend pretty much the balance of this lecture proving things are equivalence relationships, and these are some of the kinds of problems that I probably would maybe ask you to do as we go forward. So here we're going to talk about let X be the set of all non-empty subsets of this. Now this is all non-empty subsets, so you know that there's 7 sets here, and these are the non-empty subsets. So we define a relationship R on the set X as follows. For every AB in X, that is for every subset up here, A is related to B if and only if the least element of A equals the least element of B. So for example, 1, this one, is related to this one because the least element is 1 for both of those sets. Prove that this is an equivalence relationship. Well, it's reflexive because we have to, it is true to say that the least element of A equals the least element of A. Therefore, it's reflexive. It's symmetric because if you have A and B, the least element of A is the same as the least element of B, then the least element of B is the same as the least element of A. And it's transitive because you have 3 sets. If the least element of the first set is the same as the least element of the second set, and the least element of the second set is the same as the least element of the third set, the least element of the first set is the same as the least element of the third set. Therefore, it is an equivalence relationship. Now, this maybe is more interesting for computer science people. The equivalence of digital logic circuits is an equivalence relationship. Now, what does it mean? Well, we say circuit 1 is equivalent to circuit 2 if C1 has the same input-output table as C2. That means if you're putting input voltages, they come out the same way. And so if C1 is equivalent to C2 or is related to C2, then C1 is said to be equivalent to C2. And we want to prove this is an equivalence relationship. Okay, well, if certainly a circuit has the same input outputs as the same circuit has, so it is reflexive. If the first circuit has the same input outputs as the second circuit, then the second circuit certainly has the same outputs as the first circuit. And if the first and second circuits have the same input-output tables, and the second and third have the same input-output tables, then the first and the third must have the same input-output tables. So that is an equivalence relationship. And we'll return to that example in a bit. Now, certain implementations of computer languages do not place a limit on the allowable length of an identifier. That means the student, or the programmer, I guess, whenever they're programming, can use variable names of arbitrary lengths. This permits a programmer to be as precise as necessary in naming variables without having to worry about exceeding length limitations. I actually think COBOL works this way. However, compilers for such languages often ignore all but some specified number of initial characters. As far as the compiler is concerned, two identifiers are the same if they have the same initial characters, even though they may look different to the human reader of the program. For example, to a compiler that ignores all but the first 8 characters of an identifier, the following identifiers would be the same: number of screws and number of bolts. Now, if someone's reading your program, they could say, oh, I understand this a little bit better, but the computer, if it's only looking at the first 8, would stop after a number of, and these two things would be identical. Okay. Now, obviously, if you're using such a language, a programmer has to be sure to avoid using the same first characters, but the compiler lumps all these things together, and that is, in fact, a equivalence relationship. And we can prove it's an equivalence relationship because if the first 8 characters here are the same as the first 8 characters of the variable identifier, so that means it's reflexive. If the first has the same 8 characters as the second, then the second has the same 8 characters as the first in order. And if the first has the same 8 characters as the second, and the second has the same 8 characters as the third, then the first has the same 8 characters as the third, so it is transitive. So this is an equivalence relationship, and so the compiler is really thinking about equivalence classes rather than the individual statements themselves, variables themselves, variable names themselves. Okay, let's look at this. And an equivalence class of relationship can be given as a set of ordered pairs. So here we have R, and this is a relationship that exists. Now, we don't know if this is an equivalence relationship or not, and we have many ways to represent this. So we could represent this as a digraph. So here is a digraph shown of this. Now, what we've got then is, you see 0 is related to 0, so we have a loop, and 0 and 4, there's 0, 4, and there's 4, 0, so those are related. So we have that going on. And we do this whole. Now, what we do realize is we have subgraphs. So this graph doesn't overlap with this graph, and it does not overlap with that graph. But what you can do is you can go through and check all of the conditions, and this is an equivalence relationship. And if we wanted to find the distinct equivalence classes, we'd be talking about all things that are equivalent to 0, that are related to 0, 1, 2, 3, and 4, and these are other representations of the equivalence classes. So the equivalence class of 0 is the set 0, 4. The equivalence class of 1 is the set 1, 3. The equivalent class of 2 is a set containing 2, and so on. So the distinct equivalence classes are, and one of them was repeated, 1, 3 was repeated, so the distinct equivalence classes are these 3. Again, I could ask you a problem like this. When a problem asks you to find the distinct equivalence classes of an equivalence relation, you generally solve it in 2 steps. In the first step, which is what we did, you explicitly construct or imagine constructing the equivalence classes for each element, and then if there's overlaps, you can remove the overlaps. Let's return to that example we talked about, the equivalence classes of digital logic circuits. Remember, we showed that this was an equivalence relationship. So circuit C1 is equivalent to circuit C2 if C1 has the same input-output table as C2. That means that they work the same way. And so that's what this is. How many distinct equivalence classes are there? And find two different circuits that are in one of these equivalence classes. Now, we have to start with an input-output table. And so that's what we're going to do. So here is an input-output table. And you might think about this as being really a truth table, but just for digital circuits. A 1 means a high voltage, and a 0 means a low voltage level on an input. So we have inputs that are P and Q, and they give an output of R. And so if you get 1, 1, the output is 0. This defines the way the circuit's supposed to work. And so this is an input-output table, and this defines any circuit that works this way is equivalent to this. Now they ask us how many of them are there, and there are exactly many as such tables that we have, and these are binary strings of length 4. Okay, so that means that since the number of binary strings of length 4 is 2 to the 4th, or 16, there are 16 distinct input-output tables. Okay, so because each one of those can be, a true or false, but then we're combining them as well, and we got 2 inputs. So there are 2, 2, 2, 2, and 2. So there's 16 different ways that you can get the number of binary strings here. So those are distinct input-output tables. Now, that means there are exactly 16 distinct equivalence classes for these circuits. However, there are infinitely many circuits that give rise to each table. For example, this table happens if you got 2 NOT devices and an AND device following it. And here you're ORing those two because you have either path. And here you could start with an OR and go to a NOT, and you would get the same output. So this is an important example using circuits. Also, what happens is, and we talked about this before, but the relation of being congruent modulo 3, meaning you have the same remainder when you divide by 3, is symmetric and transitive. Therefore, it's an equivalence relationship. And this says that m is related to n if 3 divides evenly into m minus n. But we're supposed to describe the distinct equivalence classes of R. So what kind of values could you have? Well, you could have A, and that means that it's exactly a multiple of 3, and that means that the remainder is 0. And the equivalence class then, and all integers could be put into this. If you have a remainder of A, then that's what you get, and that's what it would look like. So we work through this, and we see that the equivalence classes then are 0, the things where there's a remainder of 0, a remainder of 1, or a remainder of 2, and those sets are, this is the one with 0 remainder, this is the one with 1 remainder, this is the remainder with 2. So you see, if we're doing these modular things, we're really saying there are only 3 equivalence classes. Now that illustrates a very important property of equivalence classes, namely that an equivalence class might have many different names. For example, on that one, the equivalence class 3 is the same thing as the equivalence class of 0, and that's the same as the equivalence class of minus 6. But they're all fall into the same equivalence class. We can think about the rational numbers, actually. That's the ratio of integers where you're not dividing by 0 are really an equivalence class as well. Because what you can say is that AB is related to CD. That is, A over B is related to C over D. We can think about that as A over B equals C over D if A times D equal B times C. This is the one of your means extremes products. So that this is an equivalence relationship, but let's prove that it's transitive, and let's talk about what are the distinct equivalence classes. Well, it's transitive because if A is related to B, then AB is equal to BC. And if AB is related to CD and CD is related to EF, then we get this expression from the first one and this expression from the second one. But then what we can do is we can multiply both sides of that equation and both sides of both those equations by B to get this, because both equal BCF. So you see this one is equal to BCF, this one is equal to BCF. So the first is equal to the third, but then we can divide all the way through by D, and we got AF is equal to BC, and that means that AB is related to EF as was to be shown. Now, there was a question B here, and so what we're really doing is we're talking about these are the numbers that are written in lowest terms. There's one equivalence class for each rational number, but 6 over 8 is the same thing as 3 over 4, and so those would fall into the same class. And a lot of mathematicians spend a lot of time, very famous mathematicians, Dedekind and Peano, spend a lot of time constructing real numbers this way in the study of logic. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.